So we've got the figure of merit that is L2 divided by F, and that's equal to the coefficient of thermal defocus minus the coefficient of thermal expansion of the outer housing divided by the coefficient of thermal expansion of the outer housing minus the coefficient of thermal expansion of the inner housing. Now, we can take this equation and rearrange it in such a way where we distribute this denominator, alpha 1 minus alpha 2 times delta minus alpha 1 divided by alpha 1 minus alpha 2. So this turns into the equation for a line where this is the slope and this is a constant that gives you an offset. So for a particular material pair 1 and 2, you can fit a particular coefficient of thermal defocus. And what you wind up seeing is the equation for a line. Now, this is actually real information from real data. And this would be the Aluminum-Delrin system. So alpha 2, or the inner housing, is Delrin, and alpha 1 is aluminum. And the slope of this line is equal to 1 divided by alpha 1 minus alpha 2. And this term, everything becomes 0 right here. So L2 over F becomes 0 at the point where the coefficient of thermal defocus is equal to the coefficient of thermal expansion of aluminum. That's that condition where the focal length is equal to the length of the outer housing. So if you want coefficient of thermal defocuses that are lower than the coefficient of thermal expansion for aluminum, actually I forgot to do this. This is 0, 100, and the units here are ppm per degree Celsius. That would be negative 100, negative 200, negative 300. 0, 1, 2, 3. So what this tells us is if you need a coefficient of thermal defocus at negative 100 ppm per degree C, you will need your L2 to be approximately 1.5 times the length of your focal length. So now we've got a way to look at a delta and understand what the length of a system would look like. So now, finally, after all that work, we're able to start to compare the curves or the lines of different material pairs. And if you do something very, very simple, like replace the aluminum with ALLVAR. So ALLVAR has a coefficient of thermal expansion of negative 30 ppm per degree C. So delta here is equal to alpha of ALLVAR Alloy 30. So the curve starts at that negative 30 ppm per degree C, moves up kind of like that. Again, where this slope is equal to 1 over the coefficient of thermal expansion of the ALLVAR minus the coefficient of thermal expansion of the Delrin. And you also notice, so in addition to the decreased slope, you also have a shifting. So you don't have to use that reentrant design for values above negative 30 ppm per degree C. And if you look at the savings or the reduction, overall it's approximately 40%. So there's about a 40% reduction in the overall length of that total athermal housing when you compare aluminum to ALLVAR for the outer housing while keeping Delrin the same for the inner housing. So if we take a look, take a step back actually, and take a look at the Aluminum-Delrin system. Again, it's bounded by the coefficient of thermal expansion of aluminum. And instead of replacing the aluminum with ALLVAR Alloy 30, we replace the Delrin with the ALLVAR Alloy 30. We see something interesting. First, the coefficient of thermal expansion of ALLVAR at negative 30 ppm per degree C is where the line starts. The slope is a lot steeper than the Aluminum-Delrin system, but you do get a region where it is still shorter than the Aluminum-Delrin system. So this is ALLVAR Alloy 30 plus aluminum. So all the way down, this is about negative 120 ppm per degree C. You still get a length savings of the ALLVAR Alloy 30 and aluminum system compared to the traditional aluminum and Delrin system. This presents some interesting and strange things. For example, you can machine ALLVAR and aluminum to much tighter tolerances than Delrin because they're alloys, and the magnitude of the thermal expansion coefficients is smaller. You can also potentially have some weight and linearity savings. But now we've got something really exciting. Because of this figure of merit that we developed, we can now start to plug in different coefficients of thermal expansion and of different materials and start to really directly compare the results. So we can have a really good understanding of not just if it's going to save in the length, but how much it's going to save.